everyone, and welcome to the Algebraic Calculus 2 course. I'm Norman Wahlberger. We'd like to move towards understanding infinite series, or better yet, ongoing series, which we are tending to call polyseries. And the exact nature of these things is a big question mark that we are trying to gently move towards. Today we're going to take some steps in that direction by starting out with a core theorem in algebra, the Binomial Theorem, and reminding you how to generalize that to the multinomial case, the Multinomial Theorem. And then we're going to move beyond that towards a much bigger picture, which is in the direction of power series or polyseries. Okay, so let me remind you that the usual binomial theorem can be expressed this way. I'll use a1 plus a2 instead of a and b, or x and y, because I'm interested in increasing the number of constituents here in the bracket. So if we have a1 plus a2 to the n, and n is here a natural number, then that's the sum from k equals 0 to n choose k, a1 to the k, a2 to the n minus k. So in this case, increasing powers of a1, decreasing powers of a2, and these familiar binomial coefficients. Now there's an interesting alternate way to write this, which is actually a little bit more conducive to generalization, which is to introduce a kind of a different kind of binomial coefficient where we have n choose k1, k2. And we can define n choose k1, k2 as being n factorial over k1 factorial, k2 factorial. And then we can re-express this by having a sum over two quantities, k1 and k2, which are natural numbers, so starting from 0, but that have the property that k1 plus k2 equals n. Then we can write it in this form where this is this new kind of binomial coefficient times a1 to the k1, a2 to the k2. So what we've really done is we've replaced the k that was sitting here with k1 and replaced the n minus k with k2. So now k1 plus k2 symmetrically add up to n. Okay, that makes it a little bit more symmetrical. And it's also a step towards expressing the multinomial theorem. So our first step in that direction is the trinomial theorem, where we have a1 plus a2 plus a3 to some power. If we square that quantity, then it's pretty familiar. Most of you will know that you get the sum of the squares of the individual constituents, a1 squared plus a2 squared plus a3 squared, plus twice the possible products, a1 times a2 plus a2 times a3 plus a1 times a3. A little bit less familiar is what happens when you cube a1 plus a2 plus a3. Well, then you get the sum of the individual cubes. You also get a let's go to this term here, a term here that's just sort of like this, where we're taking a whole bunch of products involving two of these three quantities and a third one. So a1 squared a2. So we have two a1 factors and one a2 factor. And there's 6 possible such terms. Here they all are. Okay? And this combination is multiplied by 3. So that's sort of analogous to this. And then there's an additional term, which is 6a1, a2, a3, 6 times the product of all three of them. And what is the general situation for the trinomial theorem? If you have a1 plus a2 plus a3 to the n, then you can write it as a sum of terms. Each is a power of a1 times a power of a2 times a power of a3. Say a1 to the k1, a2 to the k2, a3 to the k3. The total degree had better be n, so k1 plus k2 plus k3 equals n. And otherwise, k1 and k2 and k3 are allowed to be arbitrary natural numbers, so starting with 0. And the coefficient is a trinomial coefficient. Okay? It's n choose k1, k2, k3, which is, well, it's n factorial divided by k1 factorial, k2 factorial, k3 factorial. So, for example, say we're interested in this term here. That would be the term when k1 equals k2 equals k3 equals 1. Then this trinomial coefficient is going to be 3 choose 1 comma 1 comma 1. What's that? Well, that's 3 factorial in the numerator with a product 1 factorial, 1 factorial, 1 factorial in the denominator. So that indeed is 6. On the other hand, if we have, say, 2, 1, 0. If k1 is 2 and k2 is 1 and k3 is 0, so they still sum up to 3, then what's the coefficient? Well, then it's 3 choose 2 comma 1 comma 0. So that's going to be 3 factorial, a 6 in the numerator, and on the denominator we have a 2 factorial, a 1 factorial, and a 0 factorial. Now remind you, 0 factorial is the same as 1, so there's a total of 2 in the denominator, so 6 over 2, that's 3. That's where that 3 a1 squared a2 term is coming from. Okay, so that's the trinomial theorem. All right, so let's introduce these multinomial coefficients more generally. If n is k1 plus k2 all the way up to, say, plus k sub m, then n choose k1 comma k2 comma all the way up to k sub m is n factorial in the numerator, the product k1 factorial, k2 factorial up to km factorial in the denominator. Now actually, this condition that the sum of these terms here is equal to the n on the top is not really necessary in order to define this, but it's this particular case that's going to come up in the application to the multinomial theorem. Okay, so in this case, what does this number represent? First of all, it's not entirely obvious that this is a natural number, but it is. And we can see that by interpreting it as a count of something. So this is a count of the number of ways of choosing a certain number of objects from n objects starting out with and putting them in m boxes. So we have a bunch of objects, say n of them, and we have m boxes. Box 1, box 2, up to box m. And we're interested in putting k1 of these n's into the first box, k2 of them into the second box, and altogether then km of them into the m box, so that all of the objects here get put into boxes. So we're putting all of the objects here into these boxes. That's this condition here. And we want to know how many ways are there of doing this. If we know n and we know m and we know all these numbers k1, k2, and up to km. And I talk about this issue in my Math Foundation series, sort of earlier on in the Math Foundation, talk about the binomial theorem, the trinomial theorem, and the multinomial theorem, so you might want to remind yourself about that. But here's sort of a quick and easy way of understanding where this formula comes from. What you do is you tackle this problem in the following way. You say, okay, well, the number of ways of doing this is, first let's concentrate on putting k1 things in the first box. So there's n choose k1 ways of doing that. Okay, so they're in there. And now there's n minus k1 things left over, and we're going to choose k2 of them to put in the second box. So then we have to multiply by n minus k1, choose k2. Okay, and then the third one, okay, then there'll be n minus k1 minus k2 left, and we're choosing k3 of them to put in the third box. So we have to multiply by n minus k1 minus k2, choose 3. And we carry on like that all the way to the last box. By the time we get to the last box, there will be exactly k sub m things left. And so the number of ways of putting them in here is just km, choose km. Or if you like, n minus k1 minus k2 minus k3 minus all the way up to km minus 1. Okay? And so then if you write down those m binomial coefficients, and you sort of expand them out into factorials and do enough cancellation, then you'll see that you end up with this expression here, so that really is an integer because it really is counting the number of ways of doing this. Okay, so now we come to the multinomial theorem, which tells us how to expand a power of a general sum, a1 plus a2 all the way up to plus am, as a sum of individual terms which are all products of powers of a1 through am with some coefficients which are multinomial coefficients. So the theorem says that we're getting a sum of terms of form a1 to the k1, a2 to the k2, all the way up to am to the km, where k1 plus k2 plus km, the sum of these things here, is going to be equal to n, because the whole thing has to be of degree n. And furthermore, each of these ki's have to be natural numbers, that either 0, 1, 2, 3, etc. So we've got positive natural numbers that sum total to n. And here's that multinomial coefficient that we've just been talking about. Okay, so why is this true? Well, let me try to explain it to you here. So when you're taking a product like this, you're really, expanding out this product of n terms, each of which is a1 up to am, the sum. Okay, so we have this sum. We have n of these sums multiplied together. When we expand all of this out, okay, what's a typical term going to look like? Well, a typical term involves taking one of the terms from this expression, maybe a3. We take an a3 from that expression, and we multiply it by one of the terms here, maybe a5. And then we take one from the third one, maybe another a5, and so on. So we go through each of these n terms and pick out a single a sub I. So suppose we end up with a situation where we've altogether picked out two a1s, maybe an a1 from this box and an a1 from this box. And altogether we've picked out three a2s, and maybe one a3, and maybe five a sub m's, and some other stuff. Okay? So that's one of many possible terms that will appear. So we'd like to know, what's the coefficient of this term going to be in this big sum once we expand it all out? How many ways are there of getting exactly this term when we do all this? Well, see what that really amounts to. It's like you have these m boxes representing the a1s, the a2s, the a3s, all the way to the am's. And we're deciding in this individual case to put two of them in here, and three of them in here, and one of them in here, and something else in these guys, and five of them in there. And what actually are we putting in here? Well, we're putting in the constituent terms in this product. So there's n of these brackets, okay, n of these brackets. And let's say this a1 squared, it's coming from two out of those n brackets, maybe from this one and from this one, okay? So that's the case. We have n things, and we're choosing two of them to be in that number one box. And then we're choosing three of them to be in the two box, corresponding to the places where the a2 is being taken from, the factors that a2 is being taken from, etc. So if you think about it a little bit, okay, this is exactly the situation that I described previous slide, which is counting the number of ways of making this distribution, and that's exactly captured by this multinomial coefficient n, choose k1, k2 up to km. So that's kind of an argument of why the multinomial theorem is true. It's just a question of looking carefully at what it means to expand a product of n terms like this, where each of them has m constituents. Now, in our mathematical careers, we end up having lots of practice with binomial expansions. Not so much with more advanced or more complicated multinomial expansions. And I think it's an important skill to become familiar with, because after all, this is the algebraic calculus, and algebra and algebraic manipulations are in some sense the heart of what's going on. And a lot of things ultimately reduce to these algebraic manipulations. So having a good sense of things is really important. And this multinomial theorem is a key kind of central theoretical result. It's really good to have some understanding of it. So in the course, which I hope you'll all take at some point, we'll have lots of opportunities to investigate examples in this direction, some of them quite interesting. Okay, so but let's do a specific case here. Let's look at a1 plus a2 plus a3 plus a4 to the fifth. We want to expand this thing out. Okay, well, there's going to be a lot of terms, right? There's going to be 4 to the 5th terms, but they're some of them are going to be the same. They're going to get grouped together. So I'm expressing what we get here in this fashion here. It's a little bit incomplete, but let me explain. So this first little bracket here refers to a1 to the 5th and so on. So that means you have to kind of symmetrically extend that so that all the variables are playing the same role. So you should think about this bracket as representing a1 to the 5th plus a2 to the 5th plus a3 to the 5th plus a4 to the 5th. Okay, then it's a nice symmetric expression. The next term has a1 to the fourth a2. So it's a product of two of these things. Only two are being involved, and one of them is being involved to the fourth power and the other one to the first power. So there's a lot of those. There's a1 to the fourth times a2, a1 to the fourth times a3, a1 to the fourth times a4, a2 to the fourth times a1, a2 to the fourth times a3, etc. Okay, so that's what's all contained in the sum here, and we're saying that each one of those occurs with multiplicity 5. And then there are terms of the form a1 cubed a2 squared. Take any two of these terms, and one of them gets raised to the third power, the other one gets raised to the second power. There's 10 of them. And here we have a product of three terms, an a1 cubed times an a2 times an a3. So one of them gets raised to the third power, and the other two are just single powers. Okay, and there's 20 of each of those. Here we have a1 squared, a2 squared, a3, and all symmetric combinations of that. There's 30 of them. And here we have a1 squared, a2, a3, a4. We have 60 of them. Okay, so let's verify some of these coefficients with the multinomial theorem. So let's say this thing here, okay? So what's involved here in the coefficient of this term? This is the case when k1 is 4 and k2 is 1. Okay? So we're talking about 5 factorial over 4 factorial, 1 factorial, which is 5. This one here is 5 factorial over 3 factorial times 2 factorial, or 5 choose 3 comma 2, that's 10. This one here, 5 choose 3, 3 comma 1 comma 1, that's 5 factorial over 3 factorial, 1 factorial, 1 factorial, that's 20. This one is 30, that's 5 factorial over 2 factorial, 2 factorial, 1 factorial. And this last one, well, what would that be? That would be 5 factorial over 2 factorial times 1 factorial, 1 factorial, 1 factorial. So 120 over 2, which is indeed also 60. So that's the multinomial theorem. And it's useful to stare at something like this and sort of convince yourself you understand how it's happening. It's complicated, but it's not that complicated. There's a nice sort of structure to it. So we've expanded our view from the binomial theorem to the multinomial theorem. So a natural question is, can we go further? What would that mean? Well, can we consider a power of a sum like this where there's not 2 or 3 or 4 or 5, not a finite number of constituents in the sum, but an infinite number, like a sum that keeps on going. So a1 plus a2 plus a3 plus and so on. Well, let's think about that. I mean, if such a thing did make sense, what are we likely to get? Well, we know that if we have a finite sum, what we get is the sum of the squares of the individual constituents plus twice the sum of all possible products. So, maybe it makes sense to say, yeah, this is still going to give us something similar. We're going to get an infinite sum involving a1 squared plus a2 squared, the sum of the squares of all of these things. And then there's another term with a 2 in front that consists of all possible products. And there'll, of course, be sort of a double infinity in some sense of all possible products. So this is obviously in quotes, and we would like to understand, can we make sense of this? Does this work in some sense? I mean, sort of intuitively, we feel that something like this should exist, but what actually are we talking about? So does it make sense? Well, first of all, if we are thinking of a1, a2, and a3 as rational numbers, okay, which is often what we're doing, then the answer is no, it doesn't really make sense. And the reason is because even this initial sum is not defined. Okay, so a1 plus a2 plus a3 plus and so on is not a defined object in our arithmetic. It would be like me introducing some weird new symbol and asking, does this make sense? And you'd say, wait a minute, that's a new symbol that you haven't defined yet. So the question is meaningless. So that's the way I want you to think about it. I want you to think of a sum like this involving an infinite number of rational numbers. It's just something that is not defined. So it's not a question of whether it exists or not. It's a question of that, that addition is a binary operation. At every stage you're allowed to add one rational number to another rational number. Okay, that's what you're allowed to do. So I know that modern calculus is keen to try to circumvent this, okay? And so we're going to have a lot to say about that. But let's just, from our point of view, our position is going to be that this is not defined. However, there's an alternate way of thinking about what this might mean, and that's in terms of variables. Okay, so we could look at this and say, okay, wait a minute, what if A1 and A2 and A3 are not numbers, but are rather variables? Well, for us, variables are kind of a dubious metaphysical term, and we prefer to think about polynumbers. And I remind you that we have two polynumbers that we depend on quite a lot, alpha and beta. And we know exactly what they are, right? Alpha is like a vertical polynumber, and beta is a horizontal polynumber, and we have a nice algebra of bipolynumbers built up from alpha and beta. There's only two of them. So we could maybe relabel them and call alpha alpha 1 and beta is now alpha 2, okay? But then we would have to, in order to make something like this work, we'd have to introduce a hierarchy of additional variables or polynumbers. What would that involve? Well, that would involve taking our framework of bipolynumbers and sort of making a higher dimensional extension of it. Now that's actually a pretty interesting idea, which is one that we are going to ultimately talk a lot about. That's actually quite an important development. But it does take some doing. So one has to first establish this theory of not just polynumbers and bipolynumbers, but sort of multi-polynumbers in an ongoing setting. And so that's a major expansion of our algebra in order to sort of support this kind of statement. But it is possible, given that, to eventually look at something like this and try to interpret it in that kind of framework where both sides are representing some arithmetic with these extended polynumbers. Now this algebraic calculus course is quite novel. It's a major departure from the usual story. And I'm not trying to spend too much time criticizing the usual story here. I do that in my Math Foundations series and elsewhere to a great extent. But it is important for me to just say a few words about the inadequacies of the current framework towards infinite sums. Okay, so modern mathematics would like there to be the possibility of having infinite sums. But this is really a problematic thing of trying to define an infinite sum, a1 plus a2 plus a3, etc., of rational numbers. And one of the key problems with this is that if you try to do this in a kind of a consistent way, you'll find that the usual commutative and associative rules break down. And here's a great example which goes back to the 17th century. So, it was already well known to Leibniz and the Bernoullis, etc. So suppose you have a relatively simple sum where each of these constituents is just 1 and minus 1. So 1 plus minus 1 plus 1 plus minus 1, etc. Okay? So if you're going to treat this infinite sum something like you treat ordinary numbers, right, then associativity it should be freely available. You should be able to group these things in different ways. So in particular, you could group those first two together, 1 plus minus 1, and then the next two together, 1 plus minus 1. And if you do that, then you see that each one of these pairs is giving you 0. So you end up getting 0 plus 0 plus 0, and so on. So you have to get 0 for the value of this sum. However, if you take the same sum and you sort of use associativity and regroup them in a slightly different way. So you peel that first 1 off, and then you start grouping after that. So minus 1 plus 1 plus minus 1 plus 1. Well, then you're going to get 1 plus 0 plus 0 plus 0, etc., etc. And so you're obviously going to get 1. Okay, so how does this work? So this is an issue, a very fundamental issue with trying to add infinite numbers or infinite sets of numbers together. Okay, you run the problem that the usual laws of arithmetic break down. So modern calculus tries to get around this, and it has a whole elaborate framework for trying to do this in terms of restricting oneself to so-called convergent sums. Okay, and if you do that in the right way, then you can kind of circumvent this kind of thing. But the price that you pay for that is that you have to impose a theory of real numbers, which are sort of the pots of gold at the end of these rainbows of these convergent series that you cook up. Okay, so you have to sort of imagine this vastly more complicated and ultimately intractable arithmetic in order to support a theory of of convergence and therefore definition of infinite sums. So it's a very quick summary, okay, of why we are very very sensitive to this issue. Okay, this is a central topic. We want to address this squarely on and hold our gaze and really come to terms what the problem is and try to find a solution. Okay, I think nobody has really spent the effort in doing this, and we're going to attempt it. And our motivation is going to be those aspects of ongoing series that we've already had a look at and that we are thinking has a certain amount of consistency, namely Newton's generalized binomial series, or we're saying Newton's Polyseries theorem. Let me remind you that we considered things of the form 1 plus alpha to the r, some ongoing sum like a poly number but ongoing, so Polyseries, with coefficients h sub k of r. So r is a rational number. We're summing k equals 0 and onward, and we're getting a sum like this, 1 plus r alpha plus r times r minus 1 over 2 alpha squared, and so on. So the coefficients are like a sort of generalized binomial coefficients. And we saw that with this kind of series, there was a sense in which 1 plus alpha to the r times 1 plus alpha to the s was consistently equal to 1 plus alpha to the r plus s. This is the key result of Newton, where r and s are arbitrary rational numbers. So as a special case, if r equals s here, okay, so we're just basically squaring 1 plus alpha to the r. So we're squaring this thing here. So if we square this here, then according to this, we should get 1 plus alpha to the 2r. Okay, so we should get the same kind of series where the r is replaced with 2r. So this is a kind of an example, right, of something which is in the direction of what we're talking about. We're taking some ongoing series with an ongoing number of terms, and we're squaring it. Okay, it's not a multinomial expression. It's not a finite number of terms and we're squaring it. We have an ongoing number of terms and we're squaring it, and we're seemingly getting something. So how did we interpret this? Well, we interpreted it in the following way. We're saying, okay, what does this mean? It means that if you pick some natural number n and you look up to degree n in alpha on both sides, then you're going to get equality. So what does that mean? So it means, say, on this side here, we go up to terms of alpha to the n and we truncate or drop everything beyond that. That's going to give us a finite polynumber. Over here, if we go up to terms of degree n inside the bracket, okay, and then square that, okay, then we're going to get additional terms. But if we drop those as well beyond alpha to the n, so we end up with just an expression involving powers of alpha up to n, then those two polynumbers are going to be equal. And that should be the case for any n. So it's sort of the case that we're agreeing that we're going to have a window, a truncation window. We're only going to look at this window and ignore everything beyond. Okay, same thing here. We're going to look at this thing here and evaluate it up to a window and ignore everything beyond that. And if what we see in these two finite computable windows is the same, and that's independent of the size of the window, okay, even if the window is big, that same is going to happen, then that's what we mean by this ongoing series is equal to this ongoing series. Okay, so it's quite a departure from thinking about things in terms of arithmetic of numbers. So it's not that we're computing this and we're thinking of this as being a number. You know, this is a real number and we're squaring it, and over here there's another real number. That's not the way we're thinking about it. All right, we're thinking in this algebraic sense of in terms of truncating, going up to degree n. Or actually, since our polynumbers are generally going down, so we're going down to degree n, okay, and truncating everything below that. That's how we are going to approach the arithmetic of these infinite or ongoing series. So here is what I propose is a good framework for thinking about the extension of the multinomial theorem to having an ongoing number of constituents. The Multiseries Theorem. We're going to aim for a statement of the following kind. We're going to propose to find a formula that for an n, a natural number, if we look at this thing here, There's C0 plus C1 alpha plus C2 alpha squared and so on. I'm using C's instead of A's so that we don't get the A's and the alphas mixed up. Okay? Alpha is our favorite poly number. Okay? It's a familiar poly number. So this is an ongoing poly number or a polyseries with coefficients which are C0, C1, C2, C3, etc. And it keeps on going. And we're proposing to raise this to the nth power. And the idea is that this is going to be another polyseries. Say with coefficients D0, D1, D2, D3, etc. And we are going to want to establish a relationship like that where these coefficients over here, the d's, say d sub k, which really depends on k and also on n because we're starting with n, is some kind of function of the variables or the numbers c0, c1 up to ck. So we're proposing that we are looking for a formula where if we go up to a certain degree here, maybe up to degree 2, okay, and look at that d2, that what should happen is that d2 should be a function just of c0, c1, and c2. Right, which kind of makes sense because if we're looking just for quadratic terms, then there's no way that cubic and quartic terms involved here are going to contribute to the amount of alpha squareds on the right-hand side, right? They're not. And so we want to determine what kind of relationship is there going to be between these d's and the c's. How do we get these d sub k's as functions of the c's? And as I said before, equality here is going to be interpreted via this truncations idea in alpha. We're going to think about truncating both sides up to some arbitrary degree m. That's like our window. Okay, we're looking up to degree 2. And on this side, degree 2 on this side. Comparing what we get, it works. Good. So I'll tick off that works for 2. Then we have to demonstrate it for 3, for 4, for 5, etc. And hopefully we have some kind of inductive proof perhaps, or some kind of formula, or some kind of way of proving it for a general m. So if we can prove the equality for these finite windows of arbitrary size, and that's what we're going to mean by a statement like this. And this is going to be a great kind of thing because we're going to be able to recover the usual multinomial theorem as a kind of a special case that you get by essentially dropping a lot of the higher coefficients. So let's say we're up to CL. So we say we drop C sub L and C sub L plus 1. In other words, make them all 0. After that point, we agree that all the C's are going to be 0. Well, then that suddenly becomes then just a multinomial theorem. And then we should be able to recover the multinomial theorem by setting alpha equals 1. Okay. When we set alpha equals 1 after we've truncated, then we have finite sums in both cases, and then we hopefully will get the multinomial theorem. So we have the prospect of getting equations like this that sort of capture all of the multinomial theorems, the binomial and the trinomial and the quaternomial or whatever it is, the quintinomial, that we're capturing all of those essentially with one blow. So this is a really interesting thing to do, and the question is, well, can we do this? All right, so I suggest that there is actually cause for optimism here, because in some sense, if we're just looking at one level at a time, you're going down to a certain degree, then it's sort of reducing things to the multinomial case, and we sort of know what happens in the multinomial case. So we should be able to exploit our understanding of the multinomial case to try to come up with something. And here's what happens with n equals 3, at least initially. So suppose we have C0 plus C1 alpha plus C2 alpha squared plus, and it keeps on going, just keeps on going, and we want to cube this thing. Well, here's what you're going to get initially. In other words, here is sort of the top of this polyseries that you're going to get. The constant term is C0 cubed. Okay, so you have, imagine having these three big things that you're multiplying. The only way of getting a constant term is to take the constant term here times the constant term here times the constant term here. So we're getting C0 cubed. That's sort of obvious. And what about the alpha terms? Well, it's not hard to see that there's not a lot of ways of getting an alpha. You could take this alpha here and then that constant term and that constant term. And there's sort of 3 different ways of doing that. So you can get 3C0 squared C1 times alpha. And the quadratic term, the coefficient of alpha squared, is going to be this, 3c0 squared c2 plus 3c0 c1 squared. And the coefficient of alpha cubed is going to be 3c0 squared c3 plus 6c0 c1 c2 plus c1 cubed. You know, we can sort of feel something of the trinomial theorem there, but maybe something in addition also. And then for alpha to the fourth, well, we get these 4 terms. Alpha to the fifth, these 5 terms. And perhaps there's enough information here, so it's a good little exercise for you in sort of pattern solving and you know, just using your imagination. Can you find what the pattern is here? Okay, so in particular, for example, could you write down what you think the coefficient of alpha to the 6th is going to be? And this is optimistic because it looks like there's a pattern here to be found, and then we can hopefully jack that up. Instead of having a 3 there, we could maybe have a general n and maybe write down some multi-series theorem that goes far beyond the binomial theorem. So there's much to learn. I'm Noah Wahlberger. Thanks for listening.